Hello, explorers, and welcome to a journey back to a pivotal moment in science. We are rapidly approaching the centenary of one of humanity's most profound and baffling discoveries. A shift in understanding that completely overturned our perception of reality itself. Imagine a world where everything seemed perfectly predictable, where the universe was a grand, ticking clockwork mechanism. That was the scientific worldview at the start of 1925, a picture about to be shattered in the most spectacular way. For a decade, Albert Einstein had been the undisputed king of physics. His general theory of relativity, published in 1915, was nothing short of a revolution. It had completely supplanted the 4-century reign of Newtonian mechanics, changing our fundamental understanding of space-time motion and gravity. Space and time were no longer a static backdrop for events, but a dynamic, malleable fabric woven together into space-time, capable of being warped by matter and energy. This was a breathtaking vision. Yet, in a curious way, Einstein's revolution actually reinforced an old idea rather than overturning it. See, in the Newtonian worldview, the motion of every single particle could be perfectly computed through a simple set of universal laws. If you knew the initial conditions, you could calculate all past and all future states with absolute certainty. It was all wonderfully deterministic. And Einstein's new picture, for all its radical insights, shared this core quality. The equations of general relativity allowed for no uncertainty. The distribution of matter and energy in spacetime perfectly defined its geometry, which in turn completely determined the motion of everything within it, stretching infinitely into the past and future. Even our sense of an absolute now was destroyed with simultaneity, becoming relative, crystallizing all of time into an eternal block. The universe remained measurable and knowable, albeit from a perspective-dependent viewpoint. A hell of a perspective shift indeed, but still firmly on the side of determinism. We felt like aloof masters of a computable universe, and that feeling was about to get a serious jolt. But beneath this seemingly complete picture, there were a few pesky loose threads, like tiny knots in the otherwise smooth fabric of our understanding. For instance, the orbit of Mercury did not quite obey Newton's laws, a minor glitch Einstein famously leveraged into his grand theory. But a bigger, more mysterious thread was the strange world of the atom, especially the behavior of the humble electron. From the pioneering work of Rutherford, we knew about the rudimentary atomic nucleus. You have all seen the cartoon depictions of electrons whizzing around nuclei like miniature solar systems. That was a holdover from early assumptions that tiny universes resembled gigantic ones. But there were so many unanswered questions that plagued physicists. Why were only certain electron orbits allowed? And why those specific ones? Most puzzling of all, why did electrons not spiral into their nuclei, collapsing the atom itself? This uncanny orbit of the electron was surely the key to a new revolution. Just as the orbit of Mercury had unlocked relativity, first steps into this strange new territory were tentative. Niels Bohr building on Planck and Einstein's revolutionary idea of quantized light gave us an empirical model of quantized electron energy levels. Then Louis de Broglie, inspired by that same quantization, made a truly radical guess. He proposed that all matter, not just light, has a wave nature. Bohr then brilliantly realized that if electrons were waves, his atomic model started to make sense. The allowed orbits were those that perfectly fit an integer number of electron wave cycles, like self-reinforcing standing waves on a string. While this offered a nice story for the quantization of electron orbits, other problems persisted. Perhaps the worst was that this elegant model only worked for the simplest atom, hydrogen. So as 1925 dawned, Bohr's model still felt very classical, a patchwork quilt on a deterministic worldview. We desperately clung to the ambition of a computable universe, but the ground was already beginning to tremble. The spark that would set this entire worldview ablaze had actually begun a few years earlier in Munich, when a brilliant 20-year-old student named Werner Heisenberg showed up in the office of Arnold Sommerfeld. Sommerfeld, renowned both for his physics and his mentorship, handed the young Heisenberg a trial problem. He tasked him with solving one of the many failings of Bohr's model, specifically the distortions in hydrogen energy levels, seen when the atom was placed in strong magnetic fields. This effect was known as the anomalous Zeeman effect. Now, the thing about being a young, audacious physicist is that you will try anything. You do not yet know what you are supposed to take as ground truth. All common sense, all established wisdom dictated that the mathematical solutions should be based on integer numbers, those whole numbers of wave cycles in Bohr's electron orbits. But Sommerfeld's naive student, for whatever reason, tried a mathematical form involving physically irrelevant half-integers. And here is the kicker: it worked. This seemingly strange mathematical trick solved the problem. Young Werner Heisenberg, at just 20 years old, had discovered the first clue to the strange phase symmetry of the electron, a direct result of its yet undiscovered quantum spin. This little project ignited Heisenberg's obsession with the profound mysteries of the atom. 3 years later, in 1925, Heisenberg found himself in Göttingen, studying under the esteemed Max Born, and also in close connection with the now very famous Niels Bohr, who would become his closest collaborator. Surrounded by such giants of physics, Heisenberg still turned to the wisdom of Albert Einstein for inspiration. He asked himself, what would Einstein do? In developing general relativity, Einstein had resolved to reject all unfounded assumptions, no matter how self-evident they seemed. That meant putting aside cherished ideas like the universality of time and an unchanging flat geometry of space. So Heisenberg challenged himself to take this credo seriously and push it as far as possible into the quantum realm. In his own words, Heisenberg declared that the aim of quantum theory should be to describe only quantities which are observable. This was a radical philosophical leap. It meant making no assumptions about, for example, what the electrons are really doing inside the atom, or imagining their tiny orbits. Instead, he would build a theory entirely around the results of what we actually see when we do measurements on the atom. In a classical cartoon view of an atom, you might imagine knowing things like where an electron is or how fast it is moving at any point in time. In the Bohr model, that translated to a specific radius and an energy momentum for each orbit. A pair of concrete values, each with an index to connect them to a list of possible electron states. But Heisenberg realized that it is simply not possible to actually observe these hypothetical orbits of electrons within the atom. The only thing we can truly measure is the light, the photon that shoots out when an electron changes its state. In fact, even the very idea of orbits was presumptuous, he thought. So we will call them electron states. These invisible internal electron states could not be the main players in the new theory. Instead, Heisenberg committed to finding a law of motion that only described the observables, the frequency and the intensity or amplitude of the photon produced when electrons change states. The difference seems subtle, but it truly changed everything. Instead of a formula to describe electron properties for a single list of states, Heisenberg sought a formula to describe the resulting photon properties for every possible combination of an initial and a final state of the electron. This sort of two-index list of properties is known in mathematics as a matrix, although Heisenberg did not know that at the time. His job was to guess a formula relating these matrices, and so isolated and driven, he figured out the algebra of matrices on his own. He was quite disconcerted to discover something mathematicians already knew. That matrix algebra defies standard multiplication rules. For example, if you have two matrices X and Y, multiplying X by Y is not always the same as multiplying Y by X. They are not commutative. Imagine doing two things one after another. If the result changes depending on which one you do first, that is non-commutative. This strange mathematical property turns out to be a central feature of quantum mechanics, and ultimately led Heisenberg not only to his solution, but to the thing he is most famous for, his uncertainty principle. But for now, this unintuitive type of math was just another challenge to Heisenberg's resolution to reject prior assumptions, and so he forged ahead. Now, his new theory needed to do a couple of crucial things. It had to accurately predict the photon frequencies and intensities, the spectra of atoms. And perhaps most importantly, it also needed to be consistent with certain known fundamentals of the universe. The biggest fundamental principle of all was the principle of energy conservation. Heisenberg writes that he knew only too well that his scheme stood or fell by that principle. So Heisenberg tested his new theory as simply as he could for a physical system similar to a pendulum, the anharmonic oscillator chosen for some mathematical conveniences. If energy conservation held in this case, then his strange theory must truly be connected to the true machinery of nature. This was May 1925, and Göttingen was awash in springtime pollen, and Heisenberg's own immune system tried to kill him. He suffered a crippling attack of hay fever. It swelled his face, weakened his body, and left him barely able to multiply a matrix. He begged his boss, Max Born, for permission to travel to the one place he might find relief. A small barren island in the middle of the North Sea called Helgoland. It is an amazing place, Helgoland, sometimes also Heligoland, from the High Frisian Holy Land, with its stunning ocean cliffs and an elegant resort town. Now the war changed everything. The town was obliterated by Allied bombs targeting a Nazi U-boat harbor, and the entire tip of the island was destroyed in the largest non-nuclear man-made explosion in all of history. But Heisenberg came before all of that. He spent 10 days walking the cliffs, swimming in the ocean, and calculating his matrices, pages upon pages of them. He talks about a mounting excitement as the scheme remained self-consistent, and of how that excitement led to many mistakes that had to be fixed. And finally, on the night of June 9th, 1925, the moment arrived. Let us hear Heisenberg himself describe it. It was 3 o'clock in the morning before the final result of my computations lay before me. The energy principle had held. At first, I was deeply alarmed. I had the feeling that through the surface of atomic phenomena, I was looking at a strangely beautiful interior, and felt almost giddy at the thought that I now had to probe this wealth of mathematical structures. Nature had so generously spread out before me. I was far too excited to sleep, and so as a new day dawned, I made for the southern tip of the island and waited for the sun to rise. Cured of hay fever, but now afflicted by a profound revelation, Heisenberg returned to Göttingen. His brilliant friend Wolfgang Pauli encouraged him to show his work to Max Born, who immediately recognized Heisenberg's strange mathematics as being matrix algebra. From there, Born worked with Jordan Pasquale and then with Pauli and Paul Dirac to flesh out matrix mechanics, the very first complete formulation of quantum mechanics. But it was not the instant hit you might have imagined. It was a strange theory indeed. Matrices were unfamiliar to most physicists of the era. The non-commutativity felt alien and deeply unsettling. But perhaps worst of all, the theory seemed to tell no story of what was really happening inside the electron. The catalyzing philosophy of only consider the observables was uncomfortable for many. It was a stark departure from the intuitive visual models physicists were accustomed to. However, the scientific community, while initially resistant, was about to be offered a different path to quantum truth. Just a few months later, Erwin Schrödinger gave them something that felt far more familiar. Where Heisenberg launched his chain of thought from the quantization of energy levels, Schrödinger started with Louis de Broglie's audacious idea of particles as waves of matter. Physicists had long pondered the connection between particles and waves, and there was even a clever formulation of classical mechanics, the Hamilton-Jacobi equation, that could represent particles as waves while being formally equivalent to Newton's laws. Schrödinger, with a flash of insight, simply substituted the so-called action in this Hamilton-Jacobi equation with what we now call the wave function, leading directly to the famous Schrödinger equation. In doing so, he established wave mechanics as a powerful new way to formulate quantum mechanics. Apparently, seclusion in nature is key to quantum discoveries, because Schrödinger too was on vacation high in the Alps in the picturesque Swiss town of Arosa when he made his discovery. He had retreated there for the Christmas holidays, with, as he reports, a stack of de Broglie's papers. And with one of his many girlfriends, whose identity to this day remains a charming mystery. So perhaps not quite as secluded as Heisenberg on his barren island, but certainly an inspiring setting. Schrödinger likely came up with the final version of his seminal paper in December 1925. Schrödinger's wave mechanics was an instant sensation far more immediately popular than Heisenberg's abstract matrices. Why? Because it offered a seemingly more intuitive story of what was happening. Waves, after all, were familiar. We could visualize them, imagine them flowing and interfering. It felt like a return to some form of classical realism, a mechanism independent of the observer. Physicists eagerly embraced it, hoping it would provide a clearer, more palatable picture of the quantum world. But this comfort was short-lived. Max Born, the same Max Born who had recognized Heisenberg's matrices, soon delivered a probabilistic bombshell. He interpreted Schrödinger's wave function not as a literal wave of matter, but as a wave of probability. The square of the wave function Born proposed gave the probability of finding a particle at a certain location. This shattered any remaining hope for a purely deterministic realist interpretation. The universe, even in wave mechanics, was fundamentally probabilistic. Schrödinger himself was deeply dismayed by this probabilistic turn. He famously expressed his discomfort, saying he did not like it and was sorry he ever had anything to do with it. He had wanted to restore a classical visual understanding, and instead, his beautiful equation was revealing an even deeper level of quantum strangeness. The dream of a comfortable intuitive picture was quickly fading. The debate between wave mechanics and matrix mechanics raged briefly, but a brilliant young physicist named Paul Dirac soon brought clarity. In a stunning display of mathematical elegance, Dirac proved that matrix mechanics and wave mechanics were in fact mathematically equivalent. They were two different formulations, two different mathematical languages, describing the exact same underlying quantum reality. Two sides of the same quantum coin, seen from different yet equally valid angles. And while wave mechanics provided a more visual metaphor, Heisenberg's abstract matrix picture, with its direct focus on observables and its inherent non-commutativity, is arguably more fundamental consistent with special relativity, and naturally leading to the abstract mathematical spaces that underpin modern quantum theory. And so we arrive at the profound consequences of this revolution. The Copenhagen interpretation of quantum mechanics, developed primarily by Niels Bohr and Werner Heisenberg, solidified the radical idea that the universe between measurements is unknowable, not just in a practical sense, because you did not measure it, but in the sense of being truly undefined. It is a key fracture in the old worldview of Newton and Einstein. Matrix mechanics implied that the world is not fundamentally knowable, perhaps not even truly real in the concrete manner that we were used to between observations. This was a violent takedown of the deterministic and observer-independent Newtonian worldview. A direct consequence of matrix non-commutativity, Heisenberg soon realized, was his famed uncertainty principle. It states that there are pairs of properties of a quantum particle, like its position and its momentum, that you cannot know simultaneously with perfect precision. The more precisely you know one, the less precisely you can know the other. This is not a limitation of our measuring instruments. It is a fundamental property of nature itself. It is not that we are just bad at measuring. It is that the underlying reality itself resists such precise, simultaneous definition, And then there is the inherent randomness of quantum mechanics baked directly into the quantum laws of nature. This was perhaps the most unsettling aspect for many, including Albert Einstein, who famously declared that God does not play dice with the universe. Yet the quantum world stubbornly insisted on its probabilistic nature. Events at the quantum scale are governed by probabilities, not certainties. This shattered the deterministic dream that had reigned for centuries. The philosophical implications were staggering, the end of observer-independent reality. Profound challenges to our classical intuition about how the world works and a universe that seemed to care about whether we were looking at it or not. Despite its initial strangeness and the philosophical discomfort it engendered, quantum mechanics has proven to be an astonishingly successful theory. These strange insights from a century ago have not only stood the test of time, but have also spawned an incredible array of scientific and technological miracles. From quantum field theory to the standard model of particle physics, the fundamental understanding of matter and forces is built upon these quantum foundations. Think about it. The devices we use every day, our smartphones, computers, lasers, transistors, even nuclear power and advanced medical imaging, all owe their existence to these century-old epiphanies. Quantum mechanics works often with staggering precision, predicting experimental results with incredible accuracy. Yet despite its immense practical success and predictive power, the deepest layers of quantum reality remain in many ways less settled. The debates about the interpretations of quantum mechanics, what it truly means for reality to be undefined between measurements and the role of consciousness or observation, continue to this day. The journey initiated by a young Werner Heisenberg on a barren island pondering strange numbers and non-commutative algebra continues to inspire puzzle and challenge us. The universe, it turns out, is far stranger and more beautiful than any of us could have ever imagined. And the questions it poses are still waiting for us to explore.